Hello and welcome to a revision session from the Further Maths Support Programme. Today we're going to be looking at Edexcel Mechanics 3, and this is the second part of the Edexcel Mechanics 3 sessions that we're going to be doing. Today we're going to be looking at elasticity and oscillation. Overall, in these 4 sessions for Mechanics 3, we're going to be looking at the 4 different topics that you can see up on the screen here. If you're interested in any of the other subjects that are listed here, you'll find those in separate recordings. Today we're going to be looking at elasticity using Hooke's law, and we're going to be looking at oscillation and how elasticity can produce oscillation type questions. So let's take a look at the specification. So this is an excerpt from the Edexcel Mechanics 3 specification. It shows the topics that you need for elastic strings and springs. You need to know about Hooke's law, which we'll look at in just a moment, and you need to know about the energy stored in an elastic string or spring. And we're going to be looking at conservation of energy type questions involving those elastic strings and springs. We're also then going to move on to looking at oscillation type questions. Further dynamics covers the way that kinematics, the study of acceleration, velocity and displacement, is linked with forces, and using Newton's second law to produce equations of motion for variable forces. And we're going to look at how that works for elastic strings and springs based on the first part of the session. Okay, some definitions then that you need to be aware of, just to revise these through. By Hooke's law, the tension in an elastic string or spring when it's stretched or compressed is given by lambda x over L, where lambda is the modulus of elasticity, x is the extension or compression in a spring. You can't have compression in a string, obviously, and L is the natural length. Just notice here that the units of tension will be newtons. The units of x, the extension, are going to be meters, and the same for the natural length. So meters in the top line and meters in the bottom line here, effectively those dimensions cancel each other out, which means that lambda is measured in newtons, so modulus of elasticity here measured in newtons, and lambda measures the force required to double the length of a spring or string. We're also going to be using elastic potential energy today, and elastic potential energy measures the energy in joules that's stored in a stretched or compressed spring or in a stretched string, and you can see here that's given by lambda x squared over 2 times the natural length. Okay, so let's take a look at an example here. If you'd like to stop the recording and have a little go at this question, now is a good point to do that. I'll be starting momentarily to go through the methods required in here, so please, if you want to stop, now is the time to do it. Okay, so we're asked here to show that k equals 10. I'm just going to add a little extra information to the diagram here. I notice that because the distance AB is 2L and the system is symmetrical, that each of these 2 distances is given by L. It's useful in all mechanics questions which involve triangles to try looking at for Pythagorean triples, and you notice here we've got a right angled triangle on each side of the diagram. If you think of this distance as 3L over 4, you can think of this distance as 4L over 4, and you should be able to spot that that means that the hypotenuse here is 5L over 4, just using a little bit of Pythagoras. And that tells me that the extension in each of the 2 elastic strings involved here, the extension is going to be L over 4 because the natural length is L. So that starts to give me a little bit of information about the system here. I'm going to add some forces onto the diagram as well, noticing here that the mass of the particle is 3m rather than just m, so I know that the weight downwards is going to be 3mg. I'm also going to show the tensions in the 2 strings such as they affect the particle that we're looking at. And I'm also going to add an angle theta into the diagram just to make things a little bit easier for myself. So I know that the system is in equilibrium, so I tell the examiner that that's what I'm assuming. So in equilibrium, I know that the forces on my particle are going to balance, and I know that upwards then I've got 2 lots of the tension sine of my angle theta upwards, and that must be balanced by the weight downwards, which is given by 3mg. I can replace my sine theta in there just by looking at the triangle. My sine theta is going to be opposite over hypotenuse, which is 3/5, and that's equal to 3 mg as stated. So that gives me, just doing a little bit of rearranging, that gives me the tension in the strings is given by 5 mg over 2. And I can then bring in my Hooke's law calculation, because I know I can also calculate the tension in the string using Hooke's law. So Hooke's law T equals lambda x over L. If we substitute that information in there, we're going to have our 5 mg over 2, which is what we calculated T to be. We know that lambda is kmg. We know that x is L over 4, and the natural length is L. And you can see there that with a small amount of cancelling out, the mg's will go, the L's will go, multiply both sides by 4, and we end up with k is 10 as expected. This is the second part of the question. Again, if you'd like to pause the recording at this point and have a little go at the question yourself, that would be absolutely fine. In just a moment I will start going through the methods involved. Okay, so I'm going to add to the diagram. Please excuse my rather wobbly lines here. I don't have a straight line tool in this particular environment, but I'm going to draw in the new location of the particle down here. So this is the point it's released from. When that vertical distance there is 12L over 5, again you should be able to spot the Pythagorean triple in here that tells you that the length of the stretched string is going to be 13L over 5, and that's going to tell me that my new extension down at that lowest point there is 13L over 5 minus L, which is 8L over 5, and that's going to be useful in the calculation that I'm going to be doing here. This type of question is a classic conservation of energy question, and if you want to know how I spot that, it's by knowing that we've got variable force here, but we're only really interested in what's happening at two specific locations. We're interested in what happens when the particle's released down here, and we're interested in what happens when the particle goes through this point here at C. I'm just going to draw in the velocity that I'm looking for there, V. And any situation where you're interested in kind of one point and then a second point, but not really bothered about what happens with the forces in between, energy is a good bet for that type of question. So by conservation of energy here, I know that initially when the particle's released, there's going to be elastic potential energy in the string, but I don't need to worry about any other kind of energy at that point. When we get up to C, we're going to have kinetic energy, because we know it's moving, that's what we're looking for. It will also have gained gravitational potential energy, GPE, but as it goes through C, the string reaches its natural length, so there's no elastic potential energy remaining as the particle goes through C, so we don't need to include that in our calculation. And then the rest of the question is fairly mechanical. You just need to be super careful that you involve all of the values that you need, bearing in mind that there are two strings and that the mass of the particle is 3m rather than just m. So if I'm calculating my elastic potential energy, there are two strings, so I need two lots of lambda x squared over 2l. Lambda is 10 mg because we worked out that k equals 10. Our extension, 8l over 5, and we square that, and we divide by 2 times the natural length. That gives us an expression for our elastic potential energy. Our final kinetic energy is going to be half times 3m, remember the mass of the particle is 3m, times v squared, that's the v squared that we're looking for. And our gravitational potential energy is going to be 3mg times the height it's risen through, which we know is 12L over 5. And all of that then becomes a case of reducing the algebra down. You can cancel the m's all the way through, and with a little bit of careful rearrangement you end up with v squared is 184 over 15 times gl. So the velocity that we were looking for then is going to be the square root of all of that. I'm sorry, not 185, apologies. That should be 184. Let's just fix that. 184 gl over 15, and so we're going to take the square root of that in order to find our velocity at that point. You could give the coefficient there in as a decimal, but I think because we have the GL left in there, we don't know a value for L, I think it's reasonable to leave it as an exact fraction in that case. Okay, we're going to take a look at a different example now. We're going to look at how oscillation can be produced by simple harmonic motion, and how simple harmonic motion can come from an elastic system. Again, if you'd like to have a go at this question yourself, please do have a little read through, and then and pause and have a little read through, and I'll be beginning the solution momentarily. So I'm going to start by drawing the diagram for this one. So we're initially starting off without the object moving. We're looking at the system in equilibrium. This is my point A up here, and my point O down here where it's at its equilibrium point. Notice the particle has mass 2m, so I need to put a weight of 2mg in there, and I'm going to put a tension expression here. I always think it's worth drawing out these diagrams pretty carefully. It helps in the later part of the question where the variables get more complicated. It helps to have a good diagram to work with. So I'm drawing in here the natural length, which is 3a, and then I'm going to use an equilibrium extension, which I'm going to denote by little e here, e for equilibrium. So because that's my equilibrium extension, I'm actually going to call my tension here TE. That's my equilibrium tension. So in equilibrium, again, tell the examiner that you know what you're doing. Okay, in equilibrium we know that TE must equal 2mg for the particle to be stationary, and then we can use Hooke's law. So we know that TE equals lambda E over the natural length, which means that 2mg equals lambda is 6mg, E we're looking for, natural length is 3a, and a little rearrangement on that should quickly give you that the extension is a. Just be careful here, it asks in the question for distance AO, and I haven't actually calculated that yet. I know my equilibrium extension, but my distance AO is actually equal to 4a, 3a natural length plus the equilibrium extension a. Okay, so do be careful there. If you don't actually write that value down, obviously you will lose a mark. Okay, again, if you want to work through this question before I solve it, please have a little read through, pause at this point, and have a go at the question. I'm going to redraw my diagram with some different information on it. Again, please excuse my dodgy straight lines not being very straight. Here's my natural length. I'm going to slightly exaggerate the equilibrium extension here. You know that that equilibrium extension is A. Obviously that looks a little bit larger than the proportion of the 3a that it should be, but I'm just exaggerating that a little bit so that I can show clearly the particle at a general position. This is very important here. So this is the level of O here, this is A. It says the particle is raised to a point C vertically above A, but I'm not going to consider point C just for the time being. I'm going to consider how the particle behaves when it's a general distance x above O, above the equilibrium point there. And I know the reason I want to do this is because I want to prove my simple harmonic motion. We were talking about this in session 1 of this recording. In order to justify simple harmonic motion, I've got to show that the acceleration is proportional to the displacement from a fixed point and directed back towards that fixed point. So I'm going to have to show that by looking at the forces here in this system. I'm going to try and find a way to produce an equation of motion that looks like this, and I need to do that for a general position rather than just for a specific location of the point. Okay, let's put some forces into the diagram. Because it tells you that AC is greater than 3A, that means that the particle is released at a point that's below the natural length of the string, so it will stay in tension all the time. So there'll be a tension acting upwards, and downwards we've got our 2mg weight. So once we've got all of that information into the diagram, we can start thinking about Hooke's law, So I'm going to say at a general distance x above O, I'm going to get an expression for my tension using Hooke's law. So by Hooke's law, my T equals lambda, which is 6 mg. Now the extension in this case, do be a little bit careful here, the x in the Hooke's law formula is a different x from the x that we're using here in the equation. So in Hooke's law now we want the extension. We know that the extension to O is A, and we've gone kind of back a little bit from that, so our extension in our string at that general point is A minus x. And then Hooke's law is finished off with putting the natural length underneath. So T equals 6 mg over 3a times a minus x, and we could simplify that a little bit, perhaps expand the brackets on there. That gives me 2 mg minus 6, sorry, not 6, my mistake, 2 mg x over a, just expanding there. And now I can use my Newton's second law, because any time that we're trying to show simple harmonic motion, anytime we're trying to find an expression involving acceleration, Newton's second law is going to be our friend. We need to be extremely careful with direction here. It's very important that Newton's second law takes the direction of x increasing as the positive direction. So because this particle's been raised up to the point C, we're looking at the displacement varying, being positive in the upwards direction. Okay, so we need to consider up as positive. That means that the resultant force on the particle is going to be T minus 2 mg, and it's absolutely crucial that you get the correct direction on that part of the calculation. So because x is increasing upwards, T is in the positive x direction and 2 mg is negative. Okay, so that's our resultant force. Resultant force is mass times acceleration. Remember, our mass is 2m, so we want 2m times the acceleration on the left hand side there. We can substitute in our expression that we now know for T, 2 mg minus 2 mgx over a equals 2mx double dot. And you can see here, oh sorry, I've missed a bit there, apologies. Forgot to put the minus 2 mg in, which is kind of crucial. Okay, so yes, 2 mg minus 2 mgx over a, that's putting in the tension. We need to subtract the 2 mg, this one here, and then make it equal to 2mx double dot. And I think you can see there that this cancels away quite nicely. The 2 mg's eliminate each other, and we can divide through by 2m, and we end up with x double dot. So the acceleration is minus gx over a, and that's everything that we need to be able to justify simple harmonic motion. This is simple harmonic motion as acceleration is proportional to displacement, and also directed towards O. Okay, that tells us that we've got simple harmonic motion. It asks us to show that the period is 2 pi root a over g. Well, we can see by comparison with our classic simple harmonic formula that omega here in this case is root g over a, and our time period, just be careful not to use capital T again for period here because you've used it for tension earlier in the question. Time period is 2 pi over omega, which in this case then is going to be 2 pi times the inverse of our omega that we've got over there, 2 pi root a over g as required. Okay, so we're continuing with the same question here. We're now given that OC is a quarter A, and we have to find the greatest speed of P during the oscillation, during the motion. OC equals a quarter A. This is telling us the amplitude of the motion. Again, I'll just do a quick sketch here. 3A natural length. O is at a distance A below here. So this is my O. and you're told that it's raised up to point C, which is literally a quarter A above, and it's released from there. So the particle then is going to oscillate around O with amplitude A/4. Again, just be careful, we use the letter A to represent amplitude in this oscillation, but obviously it's being used differently here, so amplitude is A/4. And we have a nice formula for greatest speed of P. If you check out session 1 recording, we'll see this revised. Vmax, maximum velocity, is given by omega times A, and I'm just going to put that A in brackets there because that's A for amplitude. We have omega is root G over A from the previous calculation, multiplied by amplitude A/4, and that will simplify a little bit to root AG all over 4, and that's our final answer there. Okay, I hope you found that session useful. As I say, there are other recordings available for Edexcel M3 revision, and we are producing recordings for other revision modules as well. This has been produced by the Further Maths Support Programme. There's some ideas on the sorts of things that we do here on this slide, but if you want to know more about what we do, please go to www.furthermaths.org.uk. I hope you find that useful, and thank you for listening.